Okay, welcome back. So, in last class we were discussing about the different modeling approach, and I have said that what is the advantage and disadvantage of each modeling approach, and we have already covered about empirical correlation and Lagrangian track in the previous classes. Lagrangian track is the same whatever we were solving the Newton's second law of motion by taking the different forces into the account, whether it is a buoyancy, it is a drag, it is a gravity, all those forces we are balancing with the momentum. So, it is a force or with the momentum integral. So, that is what we are doing it. Now, what we are going to discuss now is the other methods, and one of the most or kind of one of the other method are kind of very initial methods which is being used for the simulation or for the modeling of the multi-phase flow is the algebraic slip method. Now, why it has been used? Because the major advantage of this model is that it is computationally very less expensive, as we are solving only one equation for both the phases. So, whether it is a continuous or dispersed phase, both the phases we solve only one equation, and we assume that the phase should be interpenetrating continuum. So, they are kind of interpenetrating each other, and we solve the equation based on the mixture properties. So, that is the algebraic slip model, and it is initially developed, and it is computationally very kind of simple, or you can say the less rigorous, and computational power requirement is less compared to the other model whatever we are going to discuss. So, let us begin with the algebraic slip model. So, what is algebraic slip model? As I said that it actually depends on the slip velocity, and we solve the algebraic equations. That is why it is called algebraic slip model, because for slip velocity we solve the algebraic equation. What we do? We solve one set of momentum equation for the mass average velocity, and we track the volume fraction of each fluid throughout the domain. So, what we do? We solve one momentum equation, one continuity equation which is based on the mass average velocity of the mixture, and what we do? We solve the volume fraction of each fluid throughout the domain. So, we are solving only one phase, one momentum, one continuity equation based on the mass average velocity, volume fraction throughout the domain. So, what we can do? We can get the velocity, we can get the your mass fraction or mass distribution, and then with the volume fraction we will get that where the phases are actually present. So, that is the whole idea of algebraic slip model, and because you are using the mass average velocity, you just need to solve only one equation for both the phases, and the mass average velocity will depend on the both the phases. We will see the equation, then it will be more clear. So, what we do here, the major assumption is an empirically derived relation for the relative velocity of the phases, and that is what I said that, and this equation is the algebraic equation which is empirically derived, and that is the major assumption, because we are going to solve the velocity based on that what is the relative velocity and slip velocity in between the two phases, and we are going to take the mass average velocity for the mixture equation, and this relative velocity formula, this relative velocity equation is actually empirically developed equation. So, your accuracy or your prediction will depend on the accuracy of this empirically derived relation, and that is the major assumption of this kind of this modeling method, and that is why the accuracy of this modeling method is not very high, particularly when the dispersed phase concentration is very high or the slip velocity is very high, and we will see that. So, for turbulent flows, again a single set of turbulent transport equations are solved. If you have the flow which is turbulent, you can solve the momentum equation, you can solve the continuity equation, you can solve the volume fraction equation, and you can solve the turbulent equation along with it. So, what will happen? You have now will increase number of equation will increase, the computational time will increase, but still at the model way it gives you the luxury to solve the turbulent flow also. This approach is actually very good for the flow fields where both the phases are generally flow in the same direction. Please mind this word generally, it is not like you cannot do the counter current, but generally it works well when both the phases are flowing in the co-current mode. It means they are flowing in the same direction. Why? Because in that way the slip velocity is actually becomes lower. So, in that this is the way overall kind of you can say that the overall approach which is being used in the algebraic slip model, one of the initially developed model which actually starts solving the multi-phase flow equation from the one dimensional to the three dimensional domain, but because the computational power was not very high, the equation was developed in this way that you can still solve this problem of the multi-phase, typical multi-phase problems, and get some solution, and we will discuss that what kind of a solution you can get from it. Overall, what you do? You solve one momentum equation, one continuity equation for based on the mass average velocity, and then you solve one equation for the volume fraction, and you solve one equation for turbulent flow if the flow is turbulent. If the flow is not turbulent, you just solve the 3 equations, and this is the reason that why your computational time is requirement is relatively lower compared to other models which we will discuss later in this course. That is the best part of this, and if you just see the equation, I am writing the equation here. This equation is for the continuity equation. If you see that this del rho upon del t term is there, this is the unsteady state mass transfer term, and this is the convective mass transfer term. So, this is dou by dou x of rho u will be equal to 0. You are getting it from the ui and xi. It means this will be in all the 3 dimensions. It will be kind of dou by dou x, del u by del x plus del v by del y plus del v by del z, or you can say that del rho un upon del x1 plus del rho u2 upon del x2 plus del rho u3 upon del x3. So, you can write it in this form, and you can solve this equation, the continuity equation. You solve the volume fraction transport equation, which was I was talking about, that how the volume fraction is being transported, because we are solving only one equation, and at the end I want that where is my gas, where is my liquid. Suppose if I am talking about a bubble column, again the same bubble column, liquid is filled, bubbles are being passed here, air is being kind of you can say dispersed, and bubble is moving. At the end I also want that where is my bubble, where is my liquid, what is the fraction of the bubble, what is the fraction of air fraction, or what is the water fraction available at any domain. So, to do that, if you do not have that information, then the solution will have very limited application. So, to get that information, we solve an additional equation here, that is the volume fraction tracking equation, and that volume fraction tracking equation actually differentiate between the phases, that which phase is there. So, because we are solving only one momentum equation and one continuity equation. So, this extra actually equation gives you the benefit or give you the luxury to separate the 2 phases and find it out that where the fractions are there. And if you see that volume fraction tracking equation is very similar to the mass conservation equation, instead of the rho we have replaced the rho with alpha, okay, in the volume fraction equation, if you will see here. So, if you see that equation, this is del alpha by del t, this is a kind of unsteady state term for the volume fraction, that how the volume fraction is changing with the time, and then this is the convective volume fraction transport term. So, how the volume fraction is being transported from one location to other location, or you say the convective motion, because of that how the kind of fraction of the phases is being transported. So, this is exactly similar to the continuity equation. The only thing is, now instead of the mass conservation or mass conservation, you are solving the volume conservation equation, or you can say that you are solving the volume transport equation instead of the mass transport equation. So, that is the way it has been written. Then we solve one momentum equation, and that momentum equation is actually based on the mixture property, mass average mixture velocities, and we also introduce a drift velocity inside, so that we can understand that what is the slip between these 2 velocity of 2 phases. So, what we do, we solve the momentum equation. If you see, this is a clear cut Navier-Stokes equation, which is I have written in the 2-dimensional domain. It is a Navier-Stokes equation, and then you add an extra term which shows that how the drift taking place between the 2 phases. So, let us discuss this term. This is the unsteady state acceleration term. This is how the particle is moving. So, del u by del t, local acceleration or unsteady state velocity term, that momentum term you can say, or local acceleration I will say, local acceleration. Okay. Then this UMI is again based on that, the mass average mixture velocity, and then you solve the convective acceleration term. This is convective term. Yeah, you solve the convective term, and then the pressure gradient is solved. That what will be the pressure gradient? This is pressure gradient. Now, this is viscous term. I have written in the 2-dimensional, that is why you are seeing the 2 thing. This is viscous force or viscous term. This is the gravity or body force. This is any extra force, any additional force which is acting on that. Please see that we have not taken the drag here, because we are solving only one equation. So, we are making the equation based on the mixture property. That is why we are not including the drag in the momentum equation term. Now, this is the term which has been extra included, so that we can get the individual information of both the phases, and that is very close to whatever the convective term is there. If you see these 2 terms, it are very close. They are the convective term The only difference is that you are now multiplying it with the alpha I. So, what you are going to do? You are going to solve all these three equations simultaneously. We are going to solve all these three equations simultaneously to get that how the individual drift is acting on each phases. That is why there is a summation time. If you have two phase, you will solve this will be the two term, one will be the for say phase 1, another term will be the same thing will be phase 2, and you will calculate this drift velocity. So, this UR is nothing but is a drift velocity. And how to calculate? So, what is there? There is more unknowns are now you have introduced two more unknowns. One is the which is the mass average mixture velocity. This is mass average mixture velocity. Mixture velocity. So, we need to define that what is this and we need to define which is nothing but the drift velocity. So, we have just modified the momentum equation, we have just added one extra term, rest of the momentum equation if you will see it is very close, is similar to the single phase flow. Only thing which is being added is this drift velocity term, which is nothing but the convective acceleration of individual phases, how the individual phases are moving, and that is why the alpha is being introduced here, so that we can have the information of the phase which we are the phase of the interest or for which we are trying to solve the problem, and then we solve the alpha overall alpha volume fraction equations, so that we can find that how the volume fraction transport is taking place. The accuracy or the unknown terms here is now is still the and that how the should be defined, how the should be defined, and as I said that the accuracy of these models depend on the definition of this and which are being defined mostly through the empirical correlations. How this rho is being defined? Because if you see here also rho is everywhere, the rho is the mixture rho, this is also rho m, this is the mixture rho. So, mixture rho is being defined as we have already discussed during the introduction phase, that the mixture rho is nothing but volume fraction of the phase 1 plus volume fraction of the phase 2. So, that is the way this mixture model, this rho is being defined, algebraic model rho mixture has been defined. Then we need to define the mass average velocity. Now, how to define the mass average velocity? So, mass average velocity has been defined by this empirical correlation, which says that it is nothing but rho alpha 1 into U1, if suppose it is a two phase, if it is two phase 1 and 2, then it will be the density of the first phase multiplied by the fraction of that phase which is present at that location for where you are solving this equation. If you are solving it numerically, you will what you will do? You will discretize the whole domain. If suppose you are doing a numerical simulation, you are going to discretize the whole domain and you will solve this equation for each cell, okay, or for each node point, depending upon what approach you are solving. You are solving the cell wise or you are solving the node wise, you will solve it, and then for each cell you will find to calculate this. So, what will happen? That alpha rho 1 is going to be remain same, that is the density of that phase 1. Alpha 1 will be changed and it will be updated through the volume transport equation for each cell and for each location and for each time. U1 will be the velocity of that phase at that location, which will be calculated. Rho 2 is nothing but that what is the density of that phase, alpha 2 again what is the hold up or volume fraction of that phase, and U2, and then it will be averaged with the mass average. We are calculating the velocity, so we have to divide by the total mass. Now, what will be the total mass per unit volume if we will take? Then it will be rho 1 into alpha 1 plus rho 2 into alpha 2, that will be the mass per unit volume. So, that is the way the mass average velocity has been calculated in these cases, and then you can use this. Here U1, U2, rho 1 and rho 2 are the velocity and density of each phases respectively. Then we calculate the drift velocity. So, how to calculate the, if you remember that the drift velocity term which we have introduced, which actually multiplied by the alpha, which shows that the phase information actually comes from that place, the individual phase information. So, the drift velocity is being defined by drift velocity is the velocity of that phase minus the velocity of mass average velocity of the mixture. So, this is mixture velocity or mass average mixture velocity, and this is the velocity of that phase, that will be the drift velocity of that phase. So, U and R, it means drift velocity, this is drift velocity of phase 1 will be equal to Un is the velocity of that phase, velocity of phase 1 minus mass averaged velocity of mixture. So, what information it gives? It gives that how much fast or how much slow this velocity, this phase is moving compared to the mass average velocity of the mixture. So, you get the individual information of that particle, and this UR you calculate, and then from UR you can get the UN. So, you can get the velocity of each phase there. And then mu is being solved with mu 1 alpha 1 plus mu 2 alpha 2, as we have already discussed that the accuracy of this equation or mu this way to calculate the effective viscosity of the mixture is always questionable, but this is the one of the best possible way to calculate the mu, or you can develop your mu reading or your mu correlation based on the experimental observation by using some viscometer. You can calculate that. The best way of calculating it is this. It may not be the all correct way or 100% correct way, but this is the one of the best way to calculate the viscosity, and you can do that with the mu 1 alpha 1 plus mu 2 alpha 2. So, what you will do now, if you will see this equation, you are almost able to know everything. Now, you can solve this and you can get the value of velocity for individual phase. So, that is the way it has been solved, and then what you do, you use some empirical correlation, because what we have not included till now is the drag. We have not included somewhere the drag, and we know that if the two phases are flowing together, one phase is in discrete, then what is going to act, the most important force is going to be the drag. So, what we need to do, we need to include the drag in our equation, then only we will be able to see the relative motion between the two phases or the slip motion between the two phases. So, the drag is being defined, that what we do, we define the relative velocity, that what will be the relative velocity or the slip velocity, and the slip velocity or relative velocity has been defined with the a bar of tau p prime. So, this is not the particle relaxation time, this is very close to particle relaxation time, that is why we have defined it as a tau p, but I put a prime so that it is looks little bit different from whatever the particle relaxation time which we have discussed earlier. So, please do not get confused, this is the particle relaxation time, but it is not purely the particle relaxation time, it is the particle relaxation time based on the drag. That is the way we define. We will cite that this is the particle relaxation time or response time based on drag. How it has been defined? There is a two term has been introduced, one is A, and these all are empirical equation, developed equation. This is A times tau p prime, and A is being defined as a overall acceleration which the particle is seeing. So, that is being the gravity. If the particle is moving or discrete phase is moving anywhere, the gravity will be acting. What is the convective acceleration which is going to take a role? So, this is dot del So, that is the convective acceleration term, and then what is the local acceleration term, del upon del t, and is being calculated, is nothing but the mass average velocity. So, that is the way we calculate the a value. If you know the you can calculate the a value very easily, then define the tau p prime. Now, again I said that we have not included the drag earlier. So, we have included the drag in the slip velocity or relative velocity, and that we are using again equation which is being empirically developed. That is the tau p prime, and tau p prime is being actually defined as rho m minus rho p, which is the mixture velocity, mixture density minus the rho of that phase, rho of particle or discrete phase, into multiply by dp square, which is nothing but the dp square is nothing but the that phase diameter or discrete phase diameter upon 18 mu f into f drag. So, we multiply it with the drag factor, and this drag factor is being calculated based on the Schiller-Norman correlation for Reynolds number less than 1000, and for the Reynolds number greater than 1000 it is being used with 0.0175 into Re. Now, you can always use your own drag, you can write a UDF or you can write your own program to use your own drag, whatever you have kind of you want to use or you feel that it will be best suited for your system, but this is the way it has been introduced. So, drag is also being introduced. So, if you will see that very smart way of modeling the thing in a simplistic solution, where you can solve very few equations. Most of the equations are, these equations are algebraic equations. So, it doesn't numerically doesn't require much time to solve, and you have only 3 equations which are coupled together and you solve it. So, all these equations you solve together to get the velocity field, to get the volume fraction field. and we have also included the drag so that we can have the idea about the slip velocity and relative velocity also. This is the way we solve the algebraic slip model equation. These are the equations which we solve it simultaneously and we get the data. The only problem or restriction is that, as I said, that we are doing, we are solving only one equation instead of the two individual equations for individual phases. Now we are solving only one equation and we are assuming that the slip velocity is not very high. You have to see that there will be several restrictions of this flow, you cannot use it, the accuracy is limited because we have oversimplified our model, accuracy is going to be limited, but it predicts well under certain conditions, and there are certain conditions it is now you cannot use it. So, the major restrictions which are there for this model, this is not only these restrictions, these are the few restrictions which are very critical and one need to be understand or one need to be careful before using this kind of approach. Is first the restriction is the particle relaxation time. The way we define the particle relaxation time, I will say that particle relaxation time based on drag, so that there should be no confusion with the initial particle relaxation time or response time the way we have defined. So, tau p prime into f drag, which is being nothing but the particle relaxation time rho m minus rho p into dp square upon 18 mu f, and should be less than 0.001 to 0.01 second. It should be in this region or it should be less than that. Why I have given two range? Because some books says this, some books follows this. So, that is why I have given both the range. It should be definitely less than this value lesser, the accuracy of the model will be much higher. But some books also say, research group also says that it should be even less than 0.01, it will be working fine. That is the way, and if you see that if I know about my system, I do not need to do the simulation, and that is why we define it in this way, that it is tau p prime into f drag, because f drag, if you want to calculate, you have to calculate the Reynolds number, for that you need the velocity inside, everything you need. So, that is why tau prime into f drag, that way, which is nothing but rho m minus rho p dp square upon 18 mu f, you can calculate all these things. Rho m can be calculated if you know that what is your kind of density of individual phases, what is the volume fraction of the individual phases, if you know the density of the discrete phase, if you know the roughly that what should be the size of your discrete phase particle or discrete phase bubble, it can be bubble, it can be droplet, it can be particle, what it will be, you can calculate the mu f if you have again some idea about the volume fraction. If it is less than 0.001, you can use this model, or less than 0.01, you can use this model, but above than that, this model applicability is really low and the accuracy will be very low. Then again, there is one limitation again, the another limitation is that one phase should be continuous and one phase should be dispersed. If two continuous phases are moving together, then it is difficult to model. So, it means if you want to model a separated flow, if suppose there is a pipe where gas and liquid are flowing, this is liquid, this is gas, okay, so this is liquid, this is gas, then you cannot use the algebraic slip model. So, one phase need to be in discrete, one or dispersed, one phase need to be continuous, okay, then only this model can be used. Then if suppose the phase is dispersed, you cannot see the interaction inside the dispersed phase. So, suppose if there is a bubble and that bubble is rotating or it is changing the shape of it, say this, and it happened with the Dankworth theory or surface renewal theory, if you will see that this is that the bubble actually keep on changing the shape, is the surface stretch theory. Those kind of interactions, if you want to model which is inside the dispersed phase, you cannot model it. Okay. Even we are not modeling anything about the bubble coalescence. So, suppose if the two bubbles are there, they are coming and close to each other and they are being form a bigger bubble. We are not modeling all those things. So, the interaction inside the dispersed phase we are not modeling. So, that is again a limitation, because most of the time in the say gas liquid system, particularly bubble column, we have seen that bubble shape, bubble size keep on changing. Okay. So, that interactions you cannot actually this cannot solve or cannot model by using the algebraic slip model. So, that is the one of the limitation. Another limitation is that the discrete phase fraction should be less than 10%, and this severely limit the application of this. Now, again there is a debate here, some people says 10%, some people says 5%. I am just citing all the numbers, I am giving you the bigger number here, it is a 10%. Definitely above than 10% you cannot do that, because discrete phase interactions will be very high. One way coupling cannot be used, you have to have two way, three way coupling at least, or four way coupling, and that is why here whatever we are doing, we are solving just one way coupling, we are solving the equation of both the phases with only coupled with the drag only. Okay, and that drag is also not the part of the main equation. Drag we are actually taking into the account in the slip velocity. Okay. So, we kind of that is the major limitation of this, that if your discrete phase fraction is more than 10%, ASM model or algebraic slip model cannot be used. And in most of the industrial problem, industrial relevant thing kind of reactors or relevant vessels, the volume fraction of discrete phase is generally more than 10% almost all the time. Okay, other than the few specialized cases, and that is why the accuracy or kind of just the model prediction is very limited. Okay, the applicability of this model is very limited. Then again, as I said, that it is desirable that both the phases should flow in the same direction, then the accuracy of the model is higher. So, this model ideally cannot be used for the counter current flow and for sedimentation flow. It means where the particles are being settled down, okay, and the fluid is moving up. In this kind of a flow, you cannot use this model, and even in case of the counter current flow, say gas is coming from the top, liquid is going from the bottom, or vice versa, gas is going from the bottom to top and liquid is coming from the top to the bottom, you cannot use this model. The accuracy of this model will be limited. So, that is the major kind of, you can say, restriction. So, I have shown here the example of a bubble column which has been solved by using the algebraic slip model, and the geometry is, there is a column, is a 2-dimensional column, okay, and what we have done, there is a small width here to show that the column can be used or the model can be used for even the 3-dimensional domain. This is the geometry, and at the center we have made a hole of certain dimensions. I think this dimension is around 1 centimeter, and we have passed the air from this. So, this whole column is filled with the liquid, this whole column is filled with the liquid, and air is passed at the center of the column by air is this passed through the center of the column. So, this is liquid and this is the air. Air is past that. So, what will happen? The air will lift at the center in the downward direction. Once the bubble will lift here at this location, okay, the velocity is very low. So, the bubble fraction is very low, bubble will lift it in this way, liquid will move upward at the center of the column, which you can see here. So, most of the bubble fraction actually will be at the center of the column. You can see here the air fraction, which is actually at the center of the column, it is showing air, the white color is actually shows air, this is air and this is liquid or water. In this case, we have taken water. So, you can see the air is flowing at the center, there is no very small amount of the air or almost no air is there near the wall, and most of the liquid is actually near the wall. This is the air, this is the water. You are able to discriminate the two phases very clearly, and that is you are able to do because you are solving the volume transport equation. So, though we are solving only one equation, we are able to discriminate between the phases, that which phase is present at what location. You can clearly see that there is more air fraction at the center, there is no air fraction or very low air fraction near the wall. We are able to differentiate between the phases, and we are able to do it. Why? Because we are solving the volume transport equation. We are able to also solve the drift equation, drift velocity equation, and we are coupling it with the slip velocities too. So, you can solve that the relative motion. Then we have also calculated the velocity of the water. Why we have not plotted the velocity of air? Because the velocity of the air will be only at the center and it will be moving upward. So, we have also tried to show the velocity of the water. This is the velocity of water, this is water velocity, and these simulations are being done in ANSYS Fluent. So, what we have the air is being passed, because air is moving up at the center of the column, water will also move up at the center of the column, and you can see that if I just zoom it, you can see that the velocity are positive at the center of the column. So, if you see this, the velocity is positive, okay, at this location you can see that the velocity is positive, okay. So, you can see this, and near the wall the velocity is negative, because what will happen if you see this location again, that near the wall the velocity is negative. And why it is happening? Because if you see positive here, it is negative velocity, negative. I do not know whether you are able to see it earlier, positive, and I zoom it, you can see this velocity is that is here the particle is moving up, and in this location the this water is actually going down. So, here liquid or water is moving up, here it is going down. Why it is moving up here? Because air is moving up or bubble is moving up that side, it is pushing some of the liquid with it, and that is why the liquid is also moving up. Then at a certain height, at this height, what happened, that air actually dispersed to the atmosphere, move out of the column and goes to the atmosphere, while liquid have not that much momentum, it have no buoyancy force, it will fall down again and then it will start coming down from this side. So, you are seeing a simple circulation cell, and we are able to predict that circulation through the ASM model. Okay. So, these are the simulations. This simulation has already been shown in the literature. We have just repeated the simulation to see that you are able to get the same profile. This is a standard way to solve the bubble column. So, if your bubble is the discrete phase volume fraction is very low, say less than 5% or 10%, you can use this column to get the information, and we have able to get those information in a very quick way or relatively faster way compared to the models which we will discuss hereafter. So, that is the advantage, but the major problem is, as I said, that the particle relaxation time multiplied by F drag should be less than 0.001 or 0.01 depending upon which group you follow. I would recommend 0.001 here. And second thing, that the flow should not be counter current and the discrete phase fraction should be less than 10% for sure. So, lower the discrete phase fraction, better the accuracy. That is the way it is kind of the model has been developed, is relatively simpler as we see in the equations, and you can solve that approach. So, that is all about the algebraic slip model which is being used. Some people also called it as a mixture model or algebraic slip model, which is being used here. I have shown here that how to kind of calculate a model in the two phase flow. In some of the kind of commercial softwares, okay, if you want to write, you can write your own course, but if you are planning to use some commercial software, be aware some of the commercial software does not allow to use more than 2 phases for ASM model. It does not mean that ASM model cannot solve 3 phase problem, it can still solve the 3 phase problem. You just need to modify the equations, you just need to modify the mixture velocity, the mixture density, mixture viscosity, the way the mass average velocity has been defined. You have to modify those equations, and it can be easily modified. The third component will be added or third phase will be added, but most of the commercial softwares actually restrict the ASM application for 2 phase flow only. So, kind of don't be confused that it can be used only for the 2 phase, it can also be used for the 3 phase. Definitely the volume fraction, if it will be 3 phase, will be further higher, interactions of the phases will be further higher. So, accuracy of the predictions will be lower, but mathematically there is no restriction, you can use it. Theoretically there is no restriction, you can use it. Okay. So, that is the overall about the algebraic slip model. Now, we will move to the next model, which is one of the most commonly used model and very popular model to model the multi-phase flow reactor, and that model name is Eulerian model. As I said earlier also in discussion, that Eulerian model, what we do, we assume all phases to be interpenetrating continuum, okay, and that is the one of the major assumption which you do. I have already discussed about that assumption, that what interpenetrating continuum means. It means suppose there is a solid phase, there is a gas phase, they are moving together, you will allow the solid to go inside the gas, you will allow the gas to go inside the solid. Physically in the real world it is not possible, but in the Euler models you show that, or you kind of describe it in that way. So, what happens for any small cell, whatever you are solving, you will not get that where is the particle exactly, where is the solid gas exactly, you will get the fraction of the solid, fraction of the gas in that cell, and that is the way the kind of the phases has been defined with the volume fraction here again, and we will multiply the equations with the volume fraction for each term, so that we can get that for each velocity, for each cell, whatever the velocity or whatever the stress we are calculating, what is the contribution of the each phases. You will see the equations, but that is the major assumption, that you assume that the particle should be interpenetrating continuum, there is no discrete nature of the particle, and that is the major limitation also, because you do that several interaction forces you cannot solve it, or you have to solve in the by using the empirically developed equation, or you have to model it by using some equation, but directly you cannot solve this, and that limits the kind of use, or you can say the accuracy of this approach. But still this is the only approach till date which can be used at all the scale. You can solve the laboratory scale problem, you can solve the pilot plant scale problem, you can solve the industrial scale problem, but only the computation time will be higher, but it has a potential to do that, and that is why this model is widely used. This model is also being known as a two fluid model, particularly if you are solving it for both the fluid phases, okay, and it is called as a two fluid model. And why two fluid model is being called because both the phases, whether it is a solid or it is a any other phase, it is a solid or it is a gas or it is a liquid, whether it is a dispersed phase, both the phases you assume to be fluid, and that is why it is also called two fluid model commonly. So, what we do in this, we solve the momentum equation and continuity equation for each phases individually. So, what we were doing earlier, we are solving only one momentum, one continuity. Here you will solve n number of momentum. If you have n number of phase, you will solve n number of momentum equation, n number of continuity equation. So, it means if I have two phase, I will solve two continuity, two momentum for both the in this kind of approach. So, what is going to happen? Your computational power requirement is going to increase, because earlier you were solving only 3, now you are going to solve 4. If you have a turbulent model, you will solve actually 5, you will also include the turbulence. If you are including the turbulence in both the phases, you are going to solve 6. So, your number of equations are increased, and that is why the computational time is higher compared to the algebraic slip model, but the accuracy is also better compared to the algebraic slip model, because now you are solving the individual equation for individual phases. Has been widely used for the modeling of fluidized bed, risers, pneumatic lines, hoppers, standpipes, particle laden flow, bubble column, slurry bubble column, all kind of a reactor. This approach has been widely used to model other than the pure granular flow, where only granules are flowing. Okay. So, that is the place where it is kind of is being not modeled, or the accuracy will be hampered, but other than that it can be used anywhere, even for the flow which is being, if the both the phases are separated, then also this model can be used. If they are dispersed, then also this model can be used. So, the applicability of this model is very wide. You can use for almost all the cases this model, and that is why the acceptability of this model is also relatively higher, because we are solving the individual phases equations, and we are coupling those equations or those phases with the drag and the other forces which will be required to solve the higher order coupling. So, we will discuss about the equation, but that is the way this whole thing is there, and it has been used for modeling all kind of a reactor. The discrete phase volume fraction can be anywhere between 0 to 60%. So, it gives you almost the luxury to solve all kind of a reactor. So, even if you solve the packed bed, generally in packed bed the maximum volume fraction goes in the range of 60%. So, you can solve till the packed bed. Even you can solve the packed bed to find that how the velocity distribution is taking place. In the trickle bed also people have used that. This gives you a lot of flexibility. If you see, the restriction of all the ASM restriction is now being removed actually, and then you can use the drag of whatever the drag you want for your system. You can write your UDF or your own code to use the drag. So, it does not restrict on your drag model. You can use the kinetic theory of granular flow, or you can based on that to solve the granular stress in the viscous regime, and it means what? It is going to solve the equation between, if you remember the closure equation, you will solve the drag if you want to do the find that the interaction between the mean motion of the solid, mean motion of the gas, or I will say mean motion of the discrete phase and mean motion of the continuous phase. You can take the turbulence equation, you can include the turbulence equation. If you want to solve the mean motion of the gas phase or the fluid phase to the fluctuating motion of the fluid phase, you can use the kinetic theory of gases if you want to solve the interactions between the mean motion of the solid phase and fluctuating motion of the solid phase. All these things you can include. You can solve the viscous regime flow, you can solve the granular stress by using the KTGF. So, that flexibility is also there, you can use that. The frictional velocity formula in the plastic regime can also be used. It means it can be used not only for the viscous regime, it can also be used for the plastic regime. You can add all the forces whatever we have discussed, whether it is virtual mass force or added mass force, it is also called virtual mass force, lift force. All these equations you can include and you can solve this. And that is why the applicability of this model is enormous, because it gives you the flexibility to do whatever you want to do. The only problem is that accuracy of all these equations, this model depends on the closure equations or the closure models which you use to solve these equations. Okay. And because these equations are now, the number of variables are more, number of equations are less, you have to use the closure equation to close that, and your accuracy of the solution now is going to depend that how good are your closure equations. So, how good are your drag force equation? We have discussed several drag forces for the same thing, for either it is a gas liquid flow, liquid flow or gas solid flow. We have discussed several type of drags. Now, depending upon how accurately your drag is able to predict the motion, it will, the accuracy of this Euler model will depend on that. How accurately the kinetic theory of granular flow models are being used to predict the fluctuations, that is the way it will able to predict the motion, or how accurately your turbulence model, whatever you are using, whether it is a K epsilon, K omega or any RNG model, whatever the accuracy, how well it is able to predict the fluctuation motion, the accuracy of the Euler model is going to depend on that. So, that is the way it has been solved, and if you use for the granular flow regime, before I go and discuss the equation. So, I said that it can be used for plastic regime, it can be used for the viscous regime for the granular flows. So, generally for the granular flow, three regimes are there, one is elastic regime, plastic regime and viscous regime. These things you might have been done in your solid mechanics course, but just for a revision I am doing it, that this Euler model can be used for these places. The elastic regimes are generally stagnant, they do not move till and their stress and strain are dependent to each other, and basically the collision is modeled with the elasticity, that how they will move, or the collision is modeled totally through the elasticity. Okay. So, that is this kind of a flow is called elastic regime. The plastic regime is where the flow is very slow, the strain rate is independent, that does not depend on that, the motion is not dependent on the strain rate, and generally the models has been, the flow models has been done through the solid mechanics. Okay, that how the solid mechanics problems we solve in the plastic regime. In the viscous regime, the flow is very fast, it moves very rapidly, okay, because they are in the viscous regime. Strain rate are dependent. Okay, so, if you change the strain rate, your overall motion will also get changed, your collision will also get changed, and the flow is mostly dependent on the kinetic theory. So, the kinetic theory of granular flow is being used to model the flow, as these flows are very much collisional dominating and they moves very fast, and strain rate is dependent. These are the three regimes. I am not going in detail of this, I am just giving you, just trying to revise it. You can see it in your solid mechanics courses, that what are the detailed of these regimes, but that is the basic classification of these three regimes. And Euler can be used for the plastic regime and viscous regime. Now, what I said that in the viscous regime, particularly most of the fluidized beds comes under the viscous regime. What we need? We need a kinetic theory of granular flow to model the collision, to model the flow actually, because the flow is depend on the kinetic theory of granular flow. Now, kinetic theory of granular flow itself is a very vast topic and cannot be covered here. So, the domain of this course is not to discuss the kinetic theory of granular flow in detail or the derivation of the kinetic theory of granular flow. You can follow any book to see that what is the, how the kinetic theory of granular flow has been defined or derived, and you will see that it is actually nothing but the kinetic theory of the granular flow is very similar to the kinetic theory of gases. You take that approach, instead of the gases, in gases kinetic theory of gases, we assume the gas molecule to be a point particles, okay, the size is infinitely small. Here we take a finite size of the particles. Now, the moment you take the finite size of the particle and the particle is being placed in the fluid which is moving, and the particles are free to move randomly anywhere, they will have the collision, and the flow will be mainly depend on the kinetic transport. It means the transport which is because of the fluid, and again the another transport which will be dominating is the transport because of the particle collision. So, that is the way the fluid particle system is being defined, and for this kind of a flow, kinetic theory of granular flow is being used and being modeled. How the kinetic theory of granular flow model has been described, this is all a brief description. Again I am telling that it is a brief description, it is very difficult to cover it in a small time, it requires substantial time to show you that how the kinetic theory of granular flow has been defined. So, basically kinetic theory of granular flow is very close to the Chapman-Scott theory. It is not very close to the actually the kinetic theory of the ideal gases or kinetic theory of gases, but it is very close to the Chapman-Scott theory, where the Chapman-Scott theory, if you remember your kinetic courses, then it has been might have been told that Chapman-Scott theory, what we do, it is for the real gas. So, you do not assume that the particle is a point particle, you assume the particle has certain size, and then you try to calculate that what will be the interaction forces will be acting on that. So, the Chapman-Scott, and then you define the attraction potential, repulsion potential, Lennard-Joule potential, all those quantities you define. Kinetic theory of granular flow also is very close to the Chapman-Scott theory, and we assume that the particle has a finite size, okay, and that particle finite size we see the interactions. So, the basically if you will see that the application of kinetic theory kinetic theory for granular flow has been developed initially by the Jenkins and Savage in 1983. Then Lun et al. Has further modified it in 1984, Ding and Gidaspo has done the same in 1990. So, this is the chronological development of this. What is based on this? This is based on the collisional particle interactions. So, what we are doing? We are seeing that how the particle will have a collision, and because of that collision, how the motion of mean motion will be correlated to the fluctuating motion of the particle. So, that is the whole idea in the kinetic theory of granular flow. So, what we do? The velocity fluctuation, what is the assumptions are that the velocity fluctuation of the solid is much smaller than their mean velocity. So, that is the one thing which we should keep in the mind, that if you are using the kinetic theory of the granular flow, your kinetic, it means the velocity fluctuations in the solid should be much lower compared to the mean velocity of the solid. If the flow is completely collisional dominating and the mean velocity of the solid is much lower than the fluctuating velocity of the solid, maybe this model will not give you the much accurate position, this kind of prediction. And why I have said this? Because some of the beds, and we will discuss it while we will discuss the binary fluidized bed and all, where you have the distribution of the particle which you use, it may possible that the flow is actually collisional dominating. We will discuss those cases where the flow, you will see that the velocity of fluctuation velocities are much higher compared to the mean velocity. So, in these kind of cases, the accuracy of the granular model predictions, the kinetic theory of granular flow will be limited. Then dissipation of the fluctuation energy due to inelastic deformation, we do that, the dissipation of the fluctuation energy due to the inelastic deformation that we take, and then dissipation also due to the friction of the particle with the fluid. So, these all dissipation we take into the account, and we use the Chapman-Scott theory model to find that what is the kinetic theory of we develop the kinetic theory of the granular flow. So, what is the major thing? This is that the particle fluctuation velocity should be less than the mean velocity. We calculate the dissipation of the fluctuation energy due to the inelastic deformation. So, particle deformation is also being taken into the account. The dissipation due to the friction of the particles with the fluid is also being taken into the account. So, all these things is taken into the account, and based on that this kinetic theory of granular flow has been developed, and a quantity has been defined that is called granular temperature. So, what we do? We take the velocity of particle is decomposed in the mean velocity and superimposed it with the fluctuation regime of fluctuating random velocity. So, we assume that there is a particle which has certain mean velocity, we superimposed that mean velocity with the random fluctuating velocity. So, that we do. Then we define a term which is very analogous to the thermodynamic temperature of the gas. When we define the kinetic theory of gas, we define the thermodynamic temperature, and how do we define the thermodynamic temperature? We define it with the collision between the particles or collision between the gas molecules, and we say that the collision between the gas molecules or the kinetic energy developed because of that collision is equal to half rho v square, and that is equal to nothing but 3/2 k T, where k is the Boltzmann constant and T is the thermodynamic temperature. So, from there you define the kinetic theory of gas, analogous to the temperature, you say 3/2 k T is equal to half m v square. So, you say that this is the kinetic theory of this, you define the kinetic energy, and you say that this kinetic energy is basically because of the collision, and that is why you feel the temperature. So, the temperature you define as 1/3 v square upon k, and if I take it the velocity as this velocity per unit mass, if I will take, or I will divide that the temperature in the mass independent quantity, if I define in that way, it will be coming it in this pies. Similar way, we define the granular temperature, which is nothing but it is associated with the random fluctuation of the fluctuating velocity of the solid particle. In the kinetic theory of gases, just go and revise it, and if there is any confusion, you can write me, we can try to resolve those problems. We assume that the particles our molecules are having a collision with each other, and they are randomly moving, and because of that random motion, their kinetic energy, because of this collision and the random motion, their kinetic energy has increased, and that is because of that only the temperature of the body will increase. So, the temperature of the body is actually related to the random motion or the kinetic energy. So, what will happen if we start heating any fluid, say gas, what will happen? Its temperature will increase. If its temperature will increase, then kinetic energy will increase, number of collision will increase. So, you can say that increase in the temperature is being seen only because of the increase in the collision. Similar thing we are also doing here in the kinetic theory of granular flow. I am not deriving it, but what we do, we take that mean velocity of the particle, we superimpose it with the fluctuating velocity, then with the analogous to the thermodynamic temperature, we define a quantity called granular temperature, and that is actually being defined as a quantity which is associated with the random fluctuation of the fluctuating velocity of the solid particle. So, what does it mean? That the fluctuating particle, whatever the particle is which is there, what is its fluctuating velocity and how the variation in the fluctuating velocity is taking place, that is the way the granular temperature has been defined, and the source of the granular temperature or the particle fluctuation is actually comes from the collision of the neighborhood particle. The particle fluctuation source, whatever we account, it is accounted based on the collision which the particle is having with the neighboring particle. So, in that way the granular temperature has been defined, and it has been defined as the exactly same way 2 upon 3 into Ks. So, suppose if I take it as a Ks, which is the kinetic energy, then it will be the temperature will be nothing but it will be 2 upon 3 of Ks divided by K. I am not including the Boltzmann constant here. So, exactly same way analogous to that, this whatever the thermodynamic temperature is being calculated or defined, analogous to that the granular temperature has been defined, which will be nothing but 2 by 3 Ks, and the Ks is nothing but the kinetic energy due to the solid velocity fluctuation per unit mass. So, I did the per unit mass, so that this m will be removed and it will be nothing but half v square. That is the Ks, kinetic energy due to the solid velocity fluctuation per unit mass. Exactly same way the kinetic energy has been defined here, that in the kinetic theory of the gases. That is why this granular temperature and the thermodynamic temperature are a very analogous quantity, and the Ks, which is the kinetic energy of fluctuation per unit mass, it will be defined as the same way. The Ks will be half, it will be V x prime square plus V y prime square plus V z prime square. So, suppose you have 3 dimensional velocity, it will be V x prime is the fluctuating velocity in x direction. So, solid fluctuating velocities, I will write it, let us make it very clear. Solid fluctuating velocity in the x direction, this is solid fluctuating velocity in the y direction, this is solid fluctuating velocity in the z direction. So, what we are saying that how the solid fluctuations are taking place in all the 3 directions, you are adding them and then you are dividing it by 1 by 2, you are square them, then add actually. So, it will be actually averaged. Okay. These all are averaged. So, what you do, suppose in a small cell, if the particle is there, 10 particles are there, you take the fluctuating velocity of all the particle, you square them and then you add them. Okay. So, that is the way it has been there. So, it is the mean fluctuating velocity of in the x direction, this is the mean solid, I will write it here, mean also, mean solid fluctuating velocity in the x direction, mean solid fluctuating velocity in the y direction, mean solid fluctuating velocity in the z direction, you take average altogether. So, that is the way the Ks has been defined, and theta is nothing but 2 by 3 of Ks, or I can say theta s is nothing but 1 upon 3, it will be V x prime square, V y prime square, V z prime square. So, that is the way the granular temperature can be defined. So, this quantity has been defined to model the collision or to predict the collision, that what will be the collision forces and how the fluctuation velocities are being correlated. Okay. So, that is the way the kinetic theory of granular flow has been defined. Again, this is a very brief way I have just tried to give the very basics of this, but what is the difference between the kinetic theory of the particle or kind of gases and the gas molecules, or kinetic theory of granular flow and kinetic theory of gases? The difference is actually whatever the difference is there between the gas molecules and the particle. So, that is the main difference between the kinetic theory of gas and kinetic theory of granular flow. That kinetic theory of the granular flow, solid particles are of few order of magnitude larger compared to the gas molecules. So, the gas molecules, even if you take the Chapman-Scott theory, we assume to the finite size of the gas molecules, but the particles are generally few order magnitude higher. So, suppose a gas molecules, even if you take a finite size, generally will be in the order of angstrom. Here you will get in the order of micrometer or nanometer. Even if you are taking nanometer particles, then also it is 1 order of magnitude higher. If you are talking about the micrometer level particle, you have 4 order magnitude higher. So, velocity fluctuation of the solids are much smaller than their mean velocity, and that is most of the time it is true, while in the case of gases it may not true, the fluctuating velocity may be higher compared to the mean velocity. The kinetic particle part of the solid fluctuation is anisotropic. Again, this is very critical. Most of the in the gas kinetic theory of the gases, we always assume that the fluctuation are isotropic in nature. It means what? Vx prime is equal to Vy prime will be equal to Vz prime, or you can say Vx prime is square, Vy prime is square, Vz prime is square is same. Any way you can define. This is the isotropic fluctuation, but whatever we get in the kinetic theory of the solids, that their fluctuation are mostly anisotropic in nature. So, if they are anisotropic, it means they are not equal. Then velocity fluctuation of the solids dissipate into heat rather fast as the result of interparticle collision. So, if you are having a collision, the particle actually the energy will dissipate very fast compared to the way it has been dissipated in the kinetic theory of gases or with the gas molecule. And granular temperature, the way we have defined, is actually the byproduct of the flow or the collisional dominating flow or byproduct of the collisional flow. That is the way we define it, and that is the difference, major difference, the way gas molecules and particles are different, or the way the kinetic theory of gases or the kinetic theory of granular flow is different. So, what we do with this, what we have done, we have defined the third or this kind of integration or third closure, and that third closure was between the particle mean motion to the particle fluctuating motion, which has been defined with the kinetic theory of granular flow and has been defined a term of this granular temperature, which will be actually correlating them. So, based on that, we will again back to the two fluid model or Euler model. Okay. So, please do not get confused, if the name is same, Euler or two fluid model. And what we do, we solve the continuity equation, we solve the momentum equation for the individual phases. So, if suppose you have a two phase, you solve the two continuity equations, say this is for the phase Q, the similar thing you will solve for the phase S. So, if they have a two phase, you will solve it in this way. The alpha is actually the volume fraction. Do not get confused, this alpha is actually whatever we are representing here, alpha is actually nothing but epsilon. So, it is the volume fraction inside, and then you solve the momentum equation. So, if you have a two phases, you solve this momentum equation and you keep or you solve it twice. So, if both the phases are liquid, you solve this equation twice. So, if you see this here again, local acceleration, convective acceleration, you solve the pressure gradient term, but now the pressure gradient is being multiplied with the volume fraction of that phase. It means now you are solving that what is the pressure difference or what is the pressure gradient, which is the contribution because of that phase. Similarly, if you see there local acceleration also we are solving, we are multiplying with the alpha, it means the phase fraction, then we are multiplying with the alpha here again. It means what? This is the contribution only of that phase. Then we solve the tau, that what is the stress, okay, viscous term, we solve this. Then any body force, definitely gravity is going to act. So, gravity on that phase, that is why we multiply here again with the alpha, and then we include a drag. So, drag is here, this is the drag, we have written the drag, we modify generally in the commercial software the drag, we write it in this way, Ks into Vs minus V, and the Ks will be defined with the rest of the term whatever the way we have discussed. So, the drag we defined as half rho A CD into slip velocity, say V minus U square. Now, what we do, they define this is as a K and V minus U, and rest of the term will be defined in terms of the K, which will be also correlated with the CD. So, we will discuss that some of these terms, but that is the way the drag has been defined, which is being acting between the two phases, and you are modeling the mean motion interaction of the two phases, which is the part of the equation now, which was not there in the algebraic slip model. In algebraic slip model, you are defining the drag, you are including the drag in the slip velocity or in the relative velocity, okay, and that you are being defined with the empirically developed correlation. Now, here we are using the model of the drag directly into the equation. So, now if suppose you have two phases, both the phases are fluid, it means say if you are solving for the gas liquid system, fluid does not mean that they should be the same phase. So, if you are solving for the gas liquid system, so the same equation once you will solve for the gas phase, once you will solve for the liquid phase. What will happen? You have two continuity equation, two momentum equation. So, that is what we solve, and then we try to find it out the closure for the drag. If you have any other interactions forces like virtual mass force, if you want to use the lift force, any other force, you can also include it here to solve this equation. So, that is what in the two fluid model or Euler model we do. Now, once the flow is solid, what we do is in case of the solid flow, in the things becomes little bit different. So, in the gas phase or both the phases which are fluid, then the things are little bit simpler. You solve exactly this equation, is a pure Navier-Stokes equation, or you can say the very close to Navier-Stokes equation, where you just include a drag force, which is the interaction between the two phases. You just multiply with the volume fraction of each phases in that place. Okay. So, the each term will be multiplied by the volume fraction, and so that if you sum both the equation, you will get the total forces which is acting on the body or within the whole kind of domain. So, that is the way it has been solved. Continuity equation is also solved individually for one individual phases. So, the mass conservation equation is always validated. You never see a problem of the mass loss, that your mass conservation is not being balanced. So, that is the major advantage. But once the solid comes into the picture, suppose now you want to solve for the gas solid or liquid solid, this equation will be modified. Okay. And some of the term will be, this equation will be modified. How this equation will be modified, we will see it here, okay, that how this equation will be modified. No, I am just erasing this, so that this equation will be more visible. So, if you see the left side of the term is not being modified, because that is nothing but the acceleration term, local acceleration, convective acceleration, they are exactly same for the solid phase also, and they are just being multiplied with the volume fraction. So, this terms has been used, okay, alpha s term. Now, we include here, if you see, there is only one pressure term. Here we include one more pressure, and that pressure is the solid pressure term. Okay. And we keep this term exactly same, alpha s into delta p, instead of this delta p alpha q or gas phase say volume fraction, now you multiply with the solid phase volume fraction, and we subtract that solid pressure term, we include that solid pressure term. Okay. Now, why the solid pressure term has been included, how it has been defined, we will discuss in the next slide. Then we use a solid stress term. Now, this is very critical, because now what we are going to model, we are going to model the delta tau s, and the tau s is being defined for the fluid with the same stress to strain dependent ratio. So, now you are treating the solid as a fluid, you are taking it as a viscous fluid, and we will see that is why you need to modify this tau s values also, and we will see those things later. So, these two terms are very critical, because you are defining it for the solid. Ideally, the solid has no viscosity, okay, or you can say that infinitely high viscosity. So, if I take the solid, if I start rubbing it, I will not deform, that is not this my fluid nature, this is not the nature of the solid. So, but what we are going to do, we are taking that viscous deformation forces here in, we are defining it in that way. So, what we need to do, we need to define the mu value of the solid. Now, mu value of the solid you cannot get, so you have to define some correlation to find the mu value of this, and that is why now you will see that though the equations looks very simple, the approach looks very simple, you need to define many quantities, and that is why the accuracy of this equation will depend the accuracy of all those models which we are using to define the solid pressure term, to solid viscosity term, the drag force term, all these terms how you are defining, your accuracy is going to be limited with that. And if you are taking the granular temperature also in, what is the terms which we are including to model the granular temperature, we will discuss that there are certain terms will be needed. This is the solid pressure term which is being defined it in this way, we will discuss anyway, I do not want to kind of get into it. So, solid pressure term, that is what this which I want to focus, that if you see that for both the fluid phase and the solid phase, the equation is same, the way it has been defined is same, and it is nothing but Newton's law of viscosity. So, if you see that, that is the way it has been defined. The only thing is being done, it has been multiplied by the alpha, so that if you are solving for the gas phase, it will tell you about the gas phase thing. If you are solving for the liquid phase, it will tell you the information about the liquid phase. So, this is the way it has been defined. This is the, if you just go and open the transport phenomena book, you will see that the tau has been defined it in this way. There is a reason to define it in this way, because the tau is a symmetric tensor. So, that is why the other transpose term has been used, so that you get the symmetric nature. The volume change can affect the viscosity, that is why this terms has been used, and if the fluid is incompressible, this del dot V term will be 0 with the continuity equation. Anyway, so this is the way it has been defined, and that is the major limitation, because the solid which cannot have any mu value, this mu value, now you need to define that mu value, and for that you need to depend on some of the equation which is being developed, and those equation accuracy will limit the accuracy of all these models. This is the, as I said, that this is nothing but a drag, and the drag is being defined. This is the interface momentum exchange or drag, which has been defined as alpha s rho s f upon tau s. Okay. So, what we have done, we have already said that, as I said, that in this force we have actually defined it in this. We have put the drag factor, we have defined the alpha s rho s upon tau p. If you will do that, you will actually get this value. Okay. And these are the forces which can be any additional force. As I said, it can be any external force, say electrical field, you can have magnetic field, it can have a lift force, it can be virtual mass force, it can be Bassett history force, any force which you want to include, you can include. So, that is the beauty of this model, it gives you lot of luxury, but the major limitation of this model is that for these things your accuracy will depend based on the accuracy of these closure equations which you are using to solve this equation. In case of the solid, the accuracy will depend on the model equation or the closure, the equations which we are using to solve the delta Ps or del Ps and del dot tau s values, and also the drag forces. We will see that how this individual terms are being defined. So, shear stress strain tensor term, as I said, that it is for the continuous phase, it has been defined, and it has been defined as mu del V plus transpose 2 upon 3 mu minus k, where k is the dilatational viscosity into del dot V I, which actually this term take care of only volume change. The dilatational viscosity is there, which is caused because of the volume change of the fluid. Some of the fluid changes the volume. This term has been included to give the symmetric nature to your this tau tensor. Tau is the second order tensor which are symmetric. To make it symmetric, the transpose term has been included, and this is the way it has been defined. Now, this is a dilatational viscosity, I have already discussed that. So, if I try to solve it in the conventional way, the way we define the tau for the fluid phase, it is being defined as minus mu dou v upon dou x into dou v x upon dou y, if it is a tau x y. Okay. So, now if you see that tau x y will be equal to tau y x. So, that does give the symmetric nature. I have removed this term because that this term will be there. This is the normal, this term identity matrix or normal this tensor, that component will be there when the normal tensor will be 1. For the shear stress term, this value is anyway going to be 0. So, that is why this value will be defined it in this way. So, this will be tau y x. If you write the tau y x, it will be also the same mu dou v x upon dou y plus dou v y upon dou x. So, this gives you the symmetric nature, and that is why this way it has been defined. For the tau x x term or the normal component of the stress, you defined it in this way. This will be dou v x plus dou v x, that is why it becomes twice of dou v x into 2 by 3 mu minus k into del dot v. These terms are, you already been knowing it, it has been well discussed in the transport phenomena. So, I am not touching it much, but that is the way the shear stress tensor in the continuous phase has been defined. So, the first part, if you see here, is not a problem to define the tau, which is the continuous phase. We can easily define that, because for that I can easily find out that what is my mu value. Okay. Now, the problem starts once you go for the solid stress tensor term. So, what happened? The solid stress tensor term we define exactly same way as the way we have defined the fluid stress tensor term. The only problem in the solid stress tensor term is now you are having a mu s, and that is going to create a problem, because solid, as I said, ideally have no viscosity, or you can say have an infinite viscosity. So, they do not move, they do not deform even for a very high strain rate. Okay. So, that is you can say either very infinite viscosity or no viscosity, the way you want to tell you can do that, but the major problem comes with the mu s. How you could define that? Dou Vs you can still find, because the gradient in the velocity will be there in the x direction, and the y direction, if there is a gradient, you will see that gradient. So, the only problem is the mu s. So, to define the mu s, several people or several researchers have given many correlations, but some of the correlations are very critical or very important. I am going to discuss that correlation only. So, the mu s actually, which is solid viscosity, has been defined. It is a summation of the three different viscosity. Okay. So, viscosity is what? It is a resistance to the flow. So, that approach has been used to define that what will be the solid shear viscosity. So, that we are trying to see that what will be the resistance force will be there if the solids are moving. So, what we are saying that resistance will be mainly because of the collision, it will be because of the kinetic energy, it will be because of the friction. These three will be there. So, the mu shear has been defined as a summation of mu collisional, mu kinetic, mu frictional. Okay. So, this is frictional. So, this is kinetic viscosity term, frictional viscosity term, and this is collisional viscosity term. It has been defined it in this way, that mu or total resistance to the flow comes because in the case of the solid will come because of the collisional viscosity, kinetic viscosity and the frictional viscosity. In that way it has been defined. For each viscosity, several equations has been proposed in the literature. Again, I am showing only those equations which are most popularly used. It does not mean that you have to limit it yourself till this point. You can develop these equations. There are several ways to develop these equations, and several equations are also available. So, we are discussing some of the tentative equations which are widely used. So, collisional viscosity equation has been defined by 4 by 5 alpha s rho s ds into, here ds is the solid diameter or diameter of the solid particle. G naught is nothing but the radial distribution function. This is radial distribution function G naught. We will discuss that. It is radial distribution function. And Es is the restitution coefficient. It is restitution coefficient. So, that is the way it has been defined, and if you see that is also the function of granular temperature. So, this theta s is nothing but it is a granular temperature. So, it says that mu collisional is going to be the proportional to under root of granular temperature. It is going to be the function of radial distribution function of the solid. It means how the solids are radially distributed. What is the restitution coefficient? Restitution coefficient has been defined that if the particles are having collision, if the collision is completely elastic, the value of ESS or restitution coefficient will be 1. If it is completely inelastic, the value will be 0. If it is viscoelastic, it means it is not completely elastic, it is not completely inelastic, the value will be between 0 to 1. Okay. So, that is the restitution coefficient. It is V prime upon V, it means the velocity of the particle after the collision to the velocity of the particle before the collision. If this is a complete elastic, both the velocity will be the same, then its value will be 1. If it is complete inelastic, then after the collision particle will actually get stationary, value will be 0. If it is viscoelastic, the value will be in between this. That is the way restitution coefficient has been defined, and the way it has been defined is that what is the fraction of the solid present at that place. What is the rho value? It means the total momentum it is going to take place, that rho value will depend. Then what is the particle size? Then what is the radial distribution of the particle? So, how the particles is being radially distributed. So, suppose this is there, how the particle radial distribution is there. Then what is the restitution coefficient of the particle? It means after the collision whether it will be stopped, whether it will be elastic, it will be inelastic. And then what is the fluctuating velocity component in the particle, and that is nothing but the granular temperature it has been included. That is the way the collisional shear viscosity term has been defined. Similarly, kinetic viscosity term has been defined. Again, I am telling again and again that these are not the only equations. There are several equations available. Don't get confused that only these equations are there. There are other equations are also available. This is the equation which is given by the Shyamlal et al. And they have also found that the mu kinetic energy is also actually the function of theta s, granular temperature. They are also going to see that what is the fluctuating velocity of the particle. They are also the function of Es, restitution coefficient, and G naught, that what is the radial distribution of the particle. Similarly, I am not detail of that how these equations are discussed. Then the viscosity is also being defined, and it is also in the same way that what is the frictional viscosity, you define with the friction and you find it out that what is the value of this. Lambda s is nothing but the bulk viscosity, which has again defined it in this way, and again if you see the bulk viscosity is very close to the way we have defined the collisional shear viscosity. These two viscosity value, if you see, other than some constant, the values are exactly same if you see these two. Why it is going to be? It means because the bulk viscosity is mainly because of the collision. So, only some parameter is being changed and you get the equation for this also. Similarly, the solid pressure, so this is the way the shear strain model is being developed. You use all these collisional equations to model that, and you see that how these equations are kind of going to be implemented in this, and the accuracy of this shear stress or kind of solid stress tensor or solid stress term will depend on how accurately these models are working. So, that is the way, and if you will see that all this value of G naught, we will discuss it, actually are being empirically defined or is being calculated based on some values or some notion like restitution coefficient values. Calculating for the solid is very different. It should, whether used for the restitution as a bulk parameter or not, the collision should be dumped at as a restitution or not. These all are different question altogether, we will discuss sometimes later, but the way it has been defined. In the next class, what I am going to do, I am going to discuss about the solid pressure term also, and then we will see that how the accuracy of the Euler model will be there, how to use that model, and then after that we will see discuss the limitation of the Euler model, and then we will use towards the Euler Lagrangian model, or which is also called a discrete phase model. Okay.